Welcome to the debate. Today, we are diving deep into one of the really intellectually compelling puzzles, I think, at the frontier of deep learning theory. And that's the fundamental nature of parametric memory in deep sequence models.
Right. We're focusing specifically on how models like, say, transformers store and retrieve these atomic facts about the world. For a long time, the default idea was just simple associations, right? But the sheer success of these massive models on structured tasks, it really suggests something far more complex is emerging inside those weights.
It really is the core debate over learned representation. I mean, it challenges our basic abstraction of what knowledge storage even means. If a model can perform reasoning that seems to require, well, structured intelligence, where and how is that structure actually encoded?
Exactly. So the central question we face is this. Does the overwhelming success that we see on implicit multi-hop reasoning tasks, these tasks requiring complex synthetic knowledge, does that necessitate the emergence of a global geometric memory?
Or is this geometry an unexpected, non-trivial phenomenon, something that's maybe actively competing with this simpler, more traditional local associative memory?
And I'll be arguing that the emergence of this robust global geometry, while it's clearly crucial to the performance we observe, it remains a profound mystery. It's not easily explained by the traditional learning pressures we usually think about, and it seems to operate in this paradoxical tension with the, let's say, default associative storage method.
And I'll be taking the position that the observable success, particularly on complex synthetic reasoning tasks, offers pretty definitive proof, actually, that a global geometric structure must prevail. That this geometric transformation is the necessary mechanism that allows these models to generalize and compress knowledge far beyond simple local co-occurrences.
Okay, so my core claim really rests on what we're calling the geometric imperative. The model's frankly robust ability to solve extremely hard implicit reasoning tasks proves that a geometric structure must dominate. Now, to test this, we use something called the in-weights path star task, and this is quite an adversarial symbolic challenge. It involves massive, complex graphs, we're talking tens of thousands of nodes, requiring the model to trace extremely long compositional paths, sometimes 10 steps deep. And it's the interpretation of why it succeeds that divides us here.
Well, precisely. Because the successful implicit reasoning we observe, specifically the perfect accuracy on the hardest prediction token, that's the very first step of that multi-hop path. It just seems logically incompatible with the simple local associative model view. Under that associative model, trying to solve a 10-step compositional task requires, well, an exponential amount of matrix manipulation. Intuitively, that would just flatten the gradient landscape, making it essentially impossible for standard gradient descent to learn efficiently. So I come at it from a different angle. The geometric memory provides the solution. How? It works by transforming the embedding space. So entity embeddings are positioned such that they encode global, multi-hop distances between them. This fundamentally changes the task, you see?
It collapses that incredibly laborious chain of 10 reasoning steps into basically a single, easy-to-learn comparison of distance in the embedding space. The model succeeds because this global geometry is the engine simplifying the optimization.
Okay, that's a compelling argument for why geometry is useful once it's there. But have you considered that the mere emergence of this powerful global geometric structure in a system that's trained solely on memorizing incompressible local atomic facts, just simple edges between nodes, is deeply counterintuitive? The geometric structure you're lauding, it doesn't seem to be driven by the typical pressures we assume necessitate organized representation. So first, let's just look at capacity pressure. We might assume, naturally, that geometry arises because maybe it's a more succinct way to store facts. Counterintuitively, our analysis shows geometry is not necessarily more compact than associative storage. The complexity gap between the two approaches, it often shrinks to just a constant factor. not something that scales dramatically with the size of the graph. And furthermore, we can actually artificially constrain the same transformer architecture to learn associatively. We can do this by freezing embeddings and the model still functions. So this demonstrates that the architecture or capacity alone doesn't compel the shift to geometry.
Second, supervisory pressure. The geometry arises even when models are trained only on local supervision, just memorizing individual edges without any explicit global objective like pathfinding. So if purely local training is sufficient to synthesize a global structured world model, then the geometry's prevalence is, well, it's a truly non-trivial phenomenon. It forces us to ask why this complex global structure is preferred over the simpler, default, local associative map. Okay, let's focus on that fundamental contradiction then in contention 1, associative hardness versus geometric ease in pathfinding. We agree on the success, right? Transformers and Mamba models can solve the in-weights path star task perfectly, even up to 10 steps of composition on these massive graphs. The critical evidence for me is that the hardest first-hop token is learned, and learned in isolation. Now, if memory were purely local and associative, learning this first token would demand the model somehow find a perfect combination of weights to perform 10 sequential matrix operations. As I said, this makes the gradient landscape functionally flat, uninformative. The sheer ability to solve that multi-hop composition task perfectly proves, I think, that a geometric re-representation must have occurred, simplifying the learning optimization from one requiring exponential time, essentially, into one solvable in constant time. The geometry provides this low-rank structure that lets the model see the entire path almost instantly.
I agree, the success is undeniable, yes. But your focus on the geometry providing an easy learning path, it overlooks a critical empirical finding regarding the optimization dynamics. If the geometric representation truly smooths the optimization landscape, as you suggest, we really should observe a clear, stepwise learning progression, what we called a reverse learning cascade.
Okay.
This cascade idea implies that tokens closest to the final answer should be learned first, right? And those insights should then cascade backward, kind of smoothing the path to learning that difficult first token. But our data shows we do not see that expected stepwise guidance. There is no reverse learning cascade. The model learns this complex composition successfully, yes, but without the expected local guidance, which makes the geometric transformation even more mysterious, actually. It's like the model is learning the answer, but the learning path doesn't follow the conceptual reasoning path we'd expect. Furthermore, consider the stark contrast between memory types here. The in-weights task, which relies on the learned parametric memory, succeeds perfectly. Yet the identical path star task, given in context, fails spectacularly. This means the model cannot use its working memory, its context window, to perform the same multi-hop reasoning it performs seamlessly using its structural parametric memory. The success rests entirely on this, well, unexplained structure you call geometry.
Right, but the profound difference between in-context failure and in-weight success is precisely why we must credit the unique high-capacity restructuring that happens within parametric memory. Contextual memory is temporary, it's sequential. Parametric memory is fixed, it's structural. The geometry is the structure that facilitates this leap. But okay, that leads us naturally to contention 2, the quality of the learned geometry.
Yes, and my issue here is really about conceptual clarity, about the integrity of the learned representation itself. If geometric memory is so fundamentally strong and necessary to solve these hard tasks, why is the geometry learned by deep sequence models, specifically the Transformer and Mamba? Why does it seem weaker and more, let's say, adulterated compared to the geometry learned by a much simpler, non-competitive architecture like Node-DVEC? When we visualize these node embeddings, the Transformer structure appears, well, noisy, compromised. This suggests to me that the inherent associative memory pathway, which is always architecturally available in a transformer, is actively competing with the geometric formation. And it's introducing noise, preventing the embedding space from achieving the pure, elegant structure we know is possible from things like Node-DVEC.
I see why you'd frame it that way, but let me offer a different perspective. I focus on the origin of the geometry, which seems to point toward a natural, intrinsic mechanism. Spectral bias.
I think this is the true underlying engine driving geometric emergence. We found that even in very simple single-layer models like Node2Vec, the training dynamics naturally push embeddings to align with the graph's Fiedler-like eigenvectors.
Sorry, the Fiedler vectors? Could you just briefly clarify that for listeners perhaps less familiar with graph theory?
Yes, certainly. So the eigenvectors of the graph Laplacian, these Fiedler-like vectors, they are essentially mathematical expressions that encode the global, most expansive structural properties of the graph. They capture global connectivity, irrespective of just local edges. Because the training dynamics naturally seem to align the embeddings with these vectors, global geometry arises organically. It happens independent of whether we explicitly constrain the space or add specific global objectives. This suggests geometry is maybe an inherent preference of gradient descent when working on graph-like data.
That's an interesting point, though. I would frame it differently. Look, the spectral analysis on Node2Vec is incredibly insightful, I grant you that. It identifies the ideal geometry, a clean, unadulterated encoding of global structure. However, that analysis doesn't model the actual competition dynamics present in a multi-layered transformer, which is explicitly designed to balance both associative retrieval and compositional ability. The fact that Node2Vec produces a more elegant geometry actually reinforces my position. The transformer's geometric ability seems inhibited, potentially by this latent competition from associative memory. The central question of how these two vastly different data structures compete under gradient descent remains unresolved, and the adulteration you see, that's the smoking gun, perhaps, of that unresolved tension.
I agree the competition is the key open question, but, in practical terms, the implications seem clear to me. Since the Node2Vec analysis shows this clear headroom for geometric quality, a level of structural purity that transformers currently don't seem to reach, practitioners should probably focus on guiding optimization to make transformer memory more geometric and less associative. This feels like the path to improving implicit reasoning and maybe enabling combinatorial creativity, the ability to discover novel, meaningful connections between bits of information scattered across vast pre-training datasets, all facilitated by the geometric encoding of global relationships.
Well, while improving geometry for generalization is certainly an appealing theoretical goal, the geometric view also imposes some inherent practical limits, I think, that practitioners really must acknowledge. Because knowledge is stored in these dense, interdependent geometric relationships, where facts are interconnected by global distance, well, it implies profound constraints on localized knowledge manipulation. Tasks like precise knowledge editing, or specific unlearning, or even just accurate atomic fact retrieval become fundamentally difficult, don't they? Because changing one embedding potentially ripples across the entire knowledge graph. So, the choice between building systems that rely heavily on parametric geometric memory versus systems that emphasize contextual in-context memory, or deciding between modern generative retrieval models and traditional dual encoder retrieval models, these choices hinge fundamentally on how we resolve this competition and understand its limits. Geometry is powerful, yes, but it might mean sacrificing a certain kind of modularity.
Ultimately, I maintain the geometric view is necessary to explain the successful, high-performing implicit reasoning we see in deep sequence models. It resolves the computational paradox of learning these hard compositional tasks by providing an elegant, low-complexity representation for global knowledge. This allows models to generalize and synthesize information far beyond simple local associations. This feels like a crucial paradigm shift that should direct new, focused research into optimizing knowledge acquisition and, indeed, embedding capacity.
Yeah, I'm still not fully convinced by that line of reasoning, primarily because the fundamental prevalence of this geometry remains deeply non-trivial. Its emergence, as I've argued, isn't easily attributable to standard architectural, capacity, or supervisory pressures. The competition, this tension between the simple, default local associative memory and the powerful global geometric memory, under the constraints of gradient descent, that remains the key open question in understanding how robust world models and high-quality representations actually emerge in these deep sequence models.
I think our debate today highlights that parametric memory is far more than just a brute force lookup table for atomic facts. It's clearly a complex, often surprising structure where global synthetic knowledge arises, seemingly, solely from training on local data. And this leaves researchers like us with profound questions about the true structural nature of learned representations in AI.
You know, we tend to think of an AI's memory as just a giant, simple database, a lookup table of facts. But what if that's completely wrong? Today, we're diving into some new research that suggests AIs are actually building these complex, geometric maps of knowledge inside their own minds. And let me tell you, it changes everything.
So we assume that when an AI learns something like Paris is the capital of France, it's just, creating a simple link between two concepts. But what if it's doing something much, much more sophisticated? This research shows that instead of just linking facts, these AIs are building intricate mental maps. And that has some pretty profound implications.
Okay, so for a long time, the leading theory for how AI stores knowledge in its core programming, what we call its parametric memory, has been this associative view. You can see it on the left. It's basically a simple lookup table. You put in Paris, it spits out France. Easy. But the theory on the right suggests something totally different, a geometric view, where the AI isn't just storing links, but it's building this rich internal map, where concepts like Paris, Eiffel Tower, and Louvre are all actual neighbors in a vast conceptual space.
So how do you even test which of these theories is right? Well, the researchers designed a really clever puzzle for a transformer model. And here's the thing, the puzzle was specifically designed to be impossible to solve if the AI was only using a simple lookup table. They basically set it up to fail.
This is a path star graph. Just think of it as a digital maze. It's got a central hub and all these long, branching paths coming off of it. Now, this maze was designed to be adversarial, which is a fancy way of saying it was built to break models that just work by predicting the next logical word or step in a sequence.
And here is the twist. The AI was never, ever shown a complete path through this maze. It was only trained on tiny individual steps. Imagine trying to teach someone how to get from New York to LA by only showing them a picture of a road sign for Chicago when they're in Des Moines and another for Denver when they're in Kansas City. You never show them the whole map.
The real test was what the paper calls an in-weights reasoning task. What that means is they gave the AI a single point way out on the edge of the maze and asked it to trace the entire path all the way back to the center, a route it had literally never seen before.
Now, for an AI using a simple associative lookup, this task is a complete nightmare. It would have to guess the first step, then guess the second, chaining together thousands of these tiny facts, one by one. It's a needle in a haystack problem that would require a nearly impossible number of computations. Everyone fully expected the model to fail.
But it didn't fail. In fact, the transformer model solved the maze, predicting these long, totally unseen paths with up to 100% accuracy. I mean, this result is just a complete knockout blow to that simple associative memory theory. So, how on earth did it do it?
Well, the answer isn't about how the AI performs step-by-step calculations. It's about how it fundamentally reorganizes the information it learns, spontaneously creating this powerful internal data structure. It's pretty amazing.
To understand this, we've got to talk about something called embeddings. See, inside an AI, a word or a concept isn't stored as text. It gets converted into a set of coordinates, an embedding, that places it at a specific point in this vast, multi-dimensional space. Think of it like a star chart, but instead of 3 dimensions, it has thousands, and the distance and direction between these points define their relationship.
And this slide just illustrates the solution brilliantly. On the left, you can see what the embeddings might look like in that old associative view, just a disorganized jumble of points, a total mess. But on the right, that's what the transformer actually did. It spontaneously created this elegant geometric map where all the nodes belonging to the same path are clustered right together.
So by creating this geometry, the AI completely transformed the problem. What was a really hard, multi-step reasoning task suddenly became a simple, one-step geometric task. To find the path, it doesn't need to chain lookups together. It just needs to see what's nearby on its own internal map. The AI isn't calculating, it's navigating.
Okay, so the AI solves the maze by creating a geometric map. This is a huge discovery, right? Case closed. Well, not quite, because this immediately leads to an even deeper, more fascinating mystery. Why? Why does it build the map this way?
Now, you might think the AI builds this map just to be more efficient, to save space, to compress the data. But, and this is the kicker, the paper proves this isn't the case. For this specific task, a simple associative lookup table would have been just as compact. There was no capacity pressure, no reason at all forcing this elegant solution.
So the model had two equally efficient paths it could have taken, and yet it consistently chose the geometric one. The paper suggests this is because of an inherent inductive bias, specifically a spectral bias, which is a really technical way of saying these models seem to have a built-in preference for finding smooth, low-frequency patterns in data, like organizing points along a clean line instead of just memorizing a jagged, chaotic list of connections. It just prefers elegance.
Now, check this out. This comparison is so interesting. On the left is the map created by our powerful transformer. On the right is a map from a much simpler model called Node2vec, which is actually forced to think geometrically. It doesn't have a choice. And notice how the simpler model's map is even cleaner, even more elegant. This suggests that even these advanced AIs like transformers aren't fully optimized for this kind of geometric thinking yet. There's still room for them to get better at it.
So, why does all this matter? I mean, this geometric view of memory isn't just some academic curiosity. It fundamentally changes how we should be thinking about AI, its hidden capabilities, and where it's all headed. Yeah, this has some huge implications. First, this geometric map could be the foundation for true creativity, allowing an AI to find surprising connections between ideas that are far apart on its map. But second, this interconnected web of knowledge might make it much harder to unlearn or edit a fact, because you can't just delete one link, you have to kind of reshape the whole map. And finally, it might explain why an AI sometimes ignores information you give it in a prompt. It trusts its own map, its own internal world model, more than what you're telling it.
So the most important takeaway here is this. AIs are not just digital filing cabinets, they are active organizers of information, independently creating these elegant, structured models of knowledge from messy, disconnected data. And we are only just beginning to scratch the surface of the incredible, emergent ways they're doing it.
And that leaves us with a pretty provocative final question, right? We now know these AIs are building these elegant geometric maps of knowledge without even being told to. It really makes you wonder, what other profound structures, what other forms of understanding are emerging inside that black box that we haven't even thought to look for yet?